go to next talk, who is also going to be in Vienna. And it's a talk by Augustin, Parjadis, Quentin, Cappart, Louis-Martin Rousseau, and David Bergman about improving branch and bound using decision diagrams and reinforcement learning.
Hello, and thank you for attending this presentation. So I am Augustin Parjadis from Polytechnique Montréal, and I'll be talking about combinatorial optimization, and especially decision diagrams and reinforcement learning for a branch and bound algorithm. So combinatorial optimization is a subfield of operations research that deals with problems that have discrete and bounded variables. Those problems are known to be hard to solve, but have a lot of applications, practical and theoretical applications in scheduling, logistics, and such. They are usually solved with some kind of branch and bound techniques. And we'll see today how decision diagrams can be used to obtain bounds on problems and to define a branch and bound algorithm. And then how reinforcement learning can be used to build more efficient decision diagrams for a more efficient search. So I'll be very quick on decision diagrams because a lot has already been presented on DDs for optimization. And here I'll be interested in the maximum independent set problem. So a problem in which, given a graph, we're trying to find a subset of non-adjacent nodes of maximum size. And I won't go into detail on how to build a decision diagram for such a problem, but you can compile a decision diagram by taking the variables of the problem one by one. And the way to read decision diagram is by taking path from the root node to the terminal node. And those will represent a solution in our original graph. So, conversely, each independent set that can be found in the graph can be represented as a path in the TT. So this is interesting, but the problem with decision diagram is the curse of dimensionality. So this states that the solution space will grow exponentially inside the size of the problem. And the solution is the decision diagram approximation. So as we saw, we can relax decision diagram by taking nodes and merging them, keeping the path that we're going in and out of those nodes. So this encodes a superset of solution of the problem because no path has been dropped, only new infeasible solutions added. And so if we were to solve it, we can obtain a dual bound on the problem. We can do the same by restricting a decision diagram by pruning a node entirely. And we obtain narrower DD that can provide a primal bound. And so with this, we can define a branch and bound scheme in which a DD is created for the problem. If that DD is too large to be compiled, we can restrict and relax it to obtain bounds, and then can branch on nodes of the relaxed decision diagram to keep the search going. And the interesting part in here is that unlike linear relaxation, the bounds obtained with decision diagram are of varying quality, depending on how they are being compiled. And we will see how that can be leveraged to have a more efficient resolution. So here is a small example of decision diagrams. Those are two decision diagrams for the same problem, for the maximum independent set over the simple path graph you can see on top. And as you can see, just by taking the variables in different order, you can have widely different diagrams, one being much narrower and easier to work with, and it will also provide a better bounds in a branch and bound algorithm. And so with that consideration, we can define a reinforcement learning environment to be able to compute good variables ordering for decision diagrams. So reinforcement learning focuses on having an agent interacting with that environment. In our case, the action the agent could take is selecting variables to be added one at a time in the decision diagram. And it does so by observing the state of the problem. In the case of the maximum independent set, the state is entirely defined by the graph of the problem. So we can use a graph neural network for our agent. It will learn to represent the graph to then select the variables, good variables to be ordering. And the agent will receive reward that quantify the impact the variable has had on the evolution of the bound. So if we can compute the difference in bound before and after adding the variable, we can have an estimation of the impact of the variable. And in the case of a lower bound, for example, in our maximization problem, we might want to encourage the growth of the bound to have a lower bound as close as possible to the optimal solution. So using such an agent in a branch and bound algorithm we need to train the agent first. So we train on graphs that have a similar distribution to those we're trying to solve. And then at each node of the branch and bound, we use the agents to build restricted and relaxed decision diagrams to obtain bounds. We need two different agents because the training process is different if we're trying to relax or restrict the decision diagram. So this is a simple approach, and this can be studied in an experiment in which I compare two branch and bound algorithms that differ only in the way the variable ordering is obtained. So either with a performance classic heuristic called min states, or minimum width, as we talked earlier, and with the reinforcement learning agents. So over random graphs, here I plot the percentage of instances that have been solved under a given number of nodes. So here, the higher the curve, the better. And as we can see, the reinforcement learning agents allow to prune the branch and bound search a lot. So a lot fewer nodes are explored during the search, which is great. But it is impractical because if we're interested in time taken, we can see that, so again, here, the higher the curve, the better, that the reinforcement learning agent take a lot of time to solve the problems. And this can be explained by the fact that feed-forward operation have to be done at each multiple time at each node of the branch and bound, which is a lot of call to the graph neural networks. But this can be improved upon. So here I define advanced integration with several small modifications. First, we'll be using the agents only for the first 100 nodes of the branch and bound search. So this is where the decision matters the most during the search. And the idea is to use that extensive variable ordering procedure only at the beginning of the search, and then using the heuristic for the remaining nodes. Only using an agent for relaxation, this is the hardest bound to close, and also crucially performing multiple actions at a time. So instead of only picking the most promising variable to be added to the DD according to the agents and doing this one at a time, we select the M most promising variables and before asking for other variables. And this makes for less precise orderings, but allows to divide by M the time taken to compute the orderings. And so here I just added the black curve. And as we can see, the number of nodes explored with those improvements is not as good as the first approach because we're computing less precise orderings, but we're still better than the heuristic. But if we are concerned by time, we can see here that this is a big improvement, and we are calling the agent much fewer times, which makes for an improvement in time also, as than in nodes. And so if we want to compare also to a simplex, to a branch and cut solver, we've been interested in much harder graphs. And here the agent, after enough graphs of size 250, we can see that again on harder graphs, the simple agent approach allows to have the fewer nodes explored during the search, and the improved version to be much faster. As we can see, the agent generalizes because on smaller graphs than those contributing training, we still have a good performance. And if we increase the size of the graph again, we can see that even though the search does not terminate after half an hour, the optimized gap is again slower with our approach. So we have shown how DD provide a flexible bounding mechanism for a combinatorial optimization problem, and how reinforcement learning can be leveraged to build more efficient decision diagrams. But this is a pretty expensive procedure, but this can be efficient if used in a crucial part of the search and efficiently. So thank you for your attention. And if you have questions, I'll be happy to help.
Any questions in Vienna?
Yes, sure.
Do you think that you can apply your work to the first talk, to the problem of the first talk?
Yeah. So learning. So we can define the branch and bound algorithm for with Western diagrams to combinatorial optimization problems in general, and the learning part for the variable ordering only depends on the decision diagram. So yeah, it could be applicable. So I've only been interested in one problem, but Quentin Cappart has also shown that you can obtain good bounds on a lot of other combinatorial optimization problems. So yes, that could be applicable. Yeah.
Thank you.
About that, so you tested on one problem, so I would buy that it works well on a problem which share a similar feature, for instance, different instances of the same problem. Have you tried exploring how generic it could be on other problems or problem families?
So not yet. This something would be interested in trying, but yeah, this has only been implemented for the maximum independent set yet.
Okay, thank you. So Peter has a question.
Yeah, I'm just, as I understand it, you're building a new decision diagram in each node in the branch and bound tree. Couldn't it be more incremental than that?
So in the way the branch and bound algorithm works, no, we actually tried keeping the ordering we used at the beginning of the search for each decision diagram developed after that, but it wasn't very efficient. And so developing a new diagram was much more interesting than this.
Okay.
So we have also one question in the chat. For the question relating this to the first talk, when issue, okay, sorry, it was an answer to Jean-Charles' comment on the first talk. One issue might be the compilation style. I believe the reinforcement learning variable ordering is for top-down compilation, whereas our method was compilation done by refinement.
Yes, this wouldn't be directly applicable because the decision diagram aren't compiled exactly the same way.
So you may discuss that in the either copy room, whether no, you're not on site. So yes. In the Discord channel. So you still have one question in Vienna?
Yes.
Yeah, no, I just just wanted to understand this. How do you decide which for ordering with graphical neural networks? Can you just explain a bit? So do you use features there, or how does
so I use the graph of the problem, and I add a feature indicating if a node has already been added to the decision diagram or not. Mm-hmm. And so this is why we have to update the graph to that feature and recall the graph neural network each time, because yeah, we give the information on the graph of which node has been selected.
Yeah. Okay, thanks.
All right. So we are going to stop the questions now, and also I think stop the decision diagram part of the session.